This video will discuss graphing quadratics using transformations. So if we take a look at this graph right here, this is the graph of y equals x squared. So I use graphing software to graph it for us, but remember, if we had a graph without a graphing utility, we would just plug numbers in. So for example, if we plugged in for x0, 0 squared is 0. So that's where all these points came from. If we plug in 1, 1 squared is 1. If we plugged in 2, 2 squared is 4. So that's how this graph gets graphed. And then remember, with parabola, there's a line of symmetry. And whatever point's on this side, there's another one on the other side, equidistance. This is 2 away, so there'd be another one 2 away. So that's how we graph a parabola. We use a table. Now there's patterns. What we call that is really transformations, depending on the numbers in the equation. So again, this is true if the highest exponent's 2. It will make this shape called a parabola. So both of these have that. However, when you're graphing in this form, so when the equation looks like this, or when it has the parentheses and then the squared, the number at the very end, the constant here, that's all by itself, we call that the k value, so this would be considered k, and this would be considered k, is going to tell you if the k value is positive, so it's like plus a number, then it's going to make the graph move up. If the k value is negative, so for example, a negative number, it's going to move the graph down that many times. So if we take a look here, the k value here is positive 1. So you can see that the graph moved up. So this is called the parent function. Think of it like it's very basic. It doesn't have any numbers other than the x squared. So if we take the parent function and we go add 1 to it, you can see that instead of having a vertex at 0, 0, it moved it up. So it moved it up 1. And then this graph right here, the k value was negative 4, and you could see that it moved the graph down 4. Okay, so that's what the number here on this at the end does. So I'm going to give us some examples here just to practice a few more. So if we take a look at these examples here that are not in your notes, we can see that the k value here is negative 3. So it's going to move the graph down 3 units. And then here it's plus 5, so it's going to move it up 5. And then here it's negative 4, so it's number at the end here without anything next to it. This is going to move the graph down 4. And this one here is going to move the graph up 1. So that's what these numbers here do. The other numbers do something else, so that's what we're going to talk about next. So the number in the parenthesis with the x, if it's a minus and then a number, it's going to, so a minus and then a number, is going to shift the graph to the right. So move it to the right. If the number in the parenthesis or with the x is a plus number, it's going to shift the graph to the left. So the reason being is the standard form, when it's in vertex form, looks like this. So for a function, so for example, this one right here, for it to become a plus, so think about this, y equals x minus, right? The standard form always has a minus. For it to be a plus, the number that h would have to be a negative 1. That's why it's going to move the graph to the negative side. It's opposite of what you would think, because for it to change to a plus, the h value was a negative 1. So the h value is always the opposite of this. That's why the graph is moving opposite of what you would think. So because this is a plus 1, you would think, oh, it should move to the positive side. But no, because of this, the number that was actually h was a negative 1. And then it made a positive. So that's why it's moving to the left. So a lot of students look at it as if it's a negative number in the parenthesis, it moves it not to the negative side, but to the positive side. So opposite of what you would think. So this problem right here has a -4 inside the parenthesis, so it's going to move it to the opposite. It's moving it to the positive side 4. So let's go ahead and take a look at a few more examples here. So this problem here does not have parentheses, so it's not going to, so it does not move left or right. Same thing here. There are no parentheses. There is no number in parentheses with x, so it does not move or shift left or right. However, this number here, this problem, or this example here, has a -2, so instead of moving it to the negative side of the graph 2, it's going to move to the right 2. And then this one has a number inside the parenthesis, and it's a +4, so it's going to move to the left 4. So right now we've talked about what the number in the parenthesis does and what the number at the end here does. These are called transformations. Okay, the last number we haven't talked about is what is the number in the front of the x squared, the leading coefficient here. What do these numbers right here? So what does the number here, if there is not 1, we know it's a 1. What effect does that number there have? So that's what we're going to talk about next. So if we take a look at these two examples here, one of them is the graph of y equals 2x squared, and one of them is the graph of y equals 1/2 x squared. So in my own words, what I would say is different about them is one looks wider, like thicker here, and this one looks skinnier. Like in my own non-mathematical terms, that's what it looks like is happening here. Also notice the graph, the value here is positive, and the graph is going up. So the first thing the number in the front, we call that the a value. So the value in the leading coefficient here. If the leading coefficient is positive, the graph will open upward. So like this. If the leading coefficient is negative, so the number in the front is negative, it will open downward. So the graph would look like that. So the number in the front, the a value, is very important. It does two things. It tells you whether the graph will open up or down. So this one will open up, and this one will open up. So they're both open upward. Okay. Not only that whether it tells you if it opens up or whether the graph goes down, it's going to also affect why this looks wider and this looks skinnier. So what we say is if the absolute value of the a value is greater than 1, so if the number here, we always think of it as a positive, if that number there as a positive is greater than 1, so this one 2 is greater than 1, the graph is going to be more stretched. So it stretches. So when we stretch, it makes it look skinnier. Okay. If the number in the front here, the leading coefficient, is between 0 and 1, okay, it should be the absolute value, is in between 0 and 1, the graph is going to shrink. And I know this is weird, but shrinking on a graph makes it look wider, actually. We'll talk about why that is in a moment here. So it has two important roles, the number in the very front. Okay, so let's talk about why they call it stretches and shrink. So if we plug in a random number for x, so for example, if we plug 2 in for x here, so if I plug in 2 and I do 2 squared, order of operations, that's 4. 4 times 2 is 8. So when I go to the graph and I go to 2, it's going to have a point all the way up here at 8. So the value of the graph just went from here and it just stretched up to 8. So the values, that's why they're using the word stretching, because this is a big stretch. The graph had a stretch up there. Whereas if we now plug in a 2 into this function, so we have 1/2, and we plug in 2 here. Exponents first, 2 squared is 4, and then half of 4 is 2. So when we plug in a 2, it doesn't stretch that much. It goes from here to here. It's not stretching as much. That's what's causing it to be wider, is the small number in the front. So the coefficient here, when it's a small number, it's going to look wider because it's not going to stretch up, causing it to look thinner. So that's why the book uses the words, or mathematicians can use the words stretches and shrink. Think of it as, if it's a small number, it's making the output smaller, causing it to look wider. Okay, so let's go ahead and take a look at our examples here. So this one is a 1, which matches this. So the parent function doesn't have a number in front, it's a 1. So since this one also has a 1, it's not going to stretch or shrink. So this one will not stretch or shrink because the number in the front, the a value here, is just 1. Now this one's a 4. That's a high number. So think about it. If you're going to end up having to multiply by 4, your output's going to get really big. So that 4 here, the a value, the 4 is going to stretch the graph. Now this one here is a small value. So it will shrink the outputs, causing it to look wider. And then this one's 13. That's going to really stretch the graph. Okay, so that's what the numbers in the equation do. So now if we take a look at the first problem here, if I graph it, you can see that it did go down 3, and it didn't go left or right. It said it doesn't move left or right, and it doesn't look stretched. It looks the same as this one, because the a value was a 1. Now, if I go put a negative in front, make the a value -1, you could see that now the graph goes down. So the number in the front is causing the graph to go up or down. So if I get rid of that negative, now the graph goes up. So that's the two roles the a value has. It makes it stretch or shrink, and it makes it go up or down. So now let's go ahead and look at the second graph. 4x squared plus 5. So we said that it should go up 5, which it does. And we wrote that it should not move left or right, so it did not move left or right. And we said that it should look stretched. It looks skinnier because of that 4 there. And the graph goes up because it's positive 4. So if I go put a -4 in the front and make the a value -4, you will see that the graph will now go down. So now if we look at the next graph here, because of the 1/2, it's a small number, it makes the graph look wider. And then you could see that the graph moves 2, because of this -2, it moves to the right 2, and then it moves down 4, the vertex. And again, if we go put a negative in the front, the graph will go down. And then lastly, that's a big number, the 13. So when we look at this graph, it should look really shrunk. So you could see that this graph is very skinny because of that large 13 that I had for the leading coefficient here. You will notice that the graph goes to the left side 4, 1, 2, 3, 4. It moves to the right, or left 4, and then it went up 1. So it followed what it should. So the point of all of this is, yes, these transformations are awesome because it tells us what the graph should look like.